The main reason that our argument here is not rigorous is that we are always trying to define a probability on this product space, which is an infinite space. Where on the other hand, we only know the meaning of uniformly randomly when the space is actually a finite space. Namely, we can only define a probability that is uniformly distributed on a finite discrete space. So, in order to make the argument rigorous, one way we could do is to start with some finite spaces, find the probability, and then take limit so that those finite spaces will approximate the full space. This is the idea. So, let me state this more carefully. We can make this rigorous by restating the problem as follows. We'll state it as the following proposition. For each positive number x, let p sub x be the probability on the space omega x defined to be pairs m, n such that m is less than or equal to x and n is also less than or equal to x, equipped with a discrete sigma algebra. Namely, every singleton is measurable, and we let this probability to be uniformly distributed. This means the probability of any singleton m, n will be equal to 1 over the cardinality of omega x. Then the proposition says the limit as x goes to infinity of the probability px of the set with pairs m, n in omega sub x such that the GCD of m, n being equal to 1 is equal to 6 over pi squared, which is approximately 61%. And we shall prove this with the following stronger result, which is due to Mertens. This is in year 1874. So, theorem. For x greater than 0, let s of x be the function that counts the number of pairs m, n, where m and n are positive integers such that m is less than or equal to x, n is less than or equal to x, and GCD of m and n is equal to 1. This can be written in another way as a summation of ones where m, n are less than or equal to x but greater than 0 with GCD of m and n equal to 1. Then we have the following asymptotic formula for s of x. S of x will be equal to 6 over pi squared times x squared plus the big omega of x times log of x, where this big notation means, say, big omega of g of x will be a function from set of positive numbers to R such that this function will be bounded by some c sub f times the absolute value of g of x for any x greater than 0, where c sub f greater than 0 is a constant depending on f. So that is a statement of Merton's theorem. And now let me show you how the theorem of Merton's implies the proposition or the probability of coprimity. Indeed, if you look at this probability that we want to study by taking limit, by using the notation of our s of x, this will equal to s of x over the cardinality of omega of x. And I claim that this number will be in the interval from s of x over the square of the seeding of x to the point s of x over the floor of x. Do you see why this is true? This can be seen with the following picture. Say your x is in here, somewhere between 2 and 3. So the floor of x and the seeding of x, squeezing this x. And there's a corresponding point on the y-axis. In this picture, x is between 2 and 3, and the cardinality of omega of x will be equal to 4, because you'll be counting those 4 points, which is squeezed between the square of x floor and the square of x seeding. And now, by the Merton's theorem, we'll divide both sides by the square of x floor or the square of x seeding, and you take the limit as x goes to infinity, because x times logarithm of x will grow much slower than the floor x squared and the seeding of x squared. You will see that s of x divided by x seeding squared and s of x divided by x floor squared both go to 6 over pi squared as x goes to infinity. From this asymptotic formula, notice that x squared divided by x seeding squared and x floor squared will both become 1 as x goes to infinity. And as a result, this probability we want to study will become 6 over pi squared when you take the limit as x goes to infinity. So the limit of this guy as x goes to infinity will be equal to 6 over pi squared. And this finishes the verification of our proposition on the probability of coprimity from Merton's theorem.